Good evening, good evening, good evening, everyone. Little mic check there if we're in chat. Can we hear okay? Right, so it's that time. It is game time. Friday is the big exam. You're sick of it. You're bored of GCSEs, but the most important exam is yet to come. So let's get to it tonight. Tonight's lesson, we are going to take a look at electricity and the basics of current electricity. We're going to run through the equations you need to know, the absolute bare minimum, and this is going to cover double award and triple award. We're going to look at circuit diagrams, how to get voltage, how to get current, how to get the information out of that. You're going to get a question on this. This is going to happen. Right, so you need to know what's going on there. And then finally, we're going to take a look at a couple of the graphs and how you work out how current voltage graphs work on that. So yes, Tegan, I'm a little bit upset about not being able to play my wee game, but I think we'll live. So on we go then with the show. You get to have a few equations to start with. First of all, you start with V equals IR, the quintessential electricity equation. This is Ohm's law. Okay, and you need to be able to state this completely correctly, which is that Ohm's law says that the current is proportional or directly proportional to the voltage applied for a conductor at constant temperature. And the constant temperature bit is important, and the spelling is terrible from the word go here today, so let's get used to it. Okay, so current is directly proportional to the voltage applied for a conductor at constant temperature. 2-mark question on that one, just if you're asked to define Ohm's law. Now, the probably most important equation that you're going to have to use is that Q is equal to I multiplied by T, and that is that the charge in coulombs is equal to the current multiplied by the time. Now, that's how it's usually phrased, but there's probably a better way of thinking about it, and that is that the current, okay, the rate of flow is the rate of flow of charge around your circuit. It's not quite the speed, but it's how much charge you get going around your circuit in a second. So it's better written as I equals Q over T, though that's harder to remember, but this is much more useful form of it. Whoop, that's a circle. We don't want one of them. We want one of these. Okay, so this one here is what we're after in terms of talking about physics, because when you're talking about current, what you're actually talking about is the amount of charge that you've got going round your circuit. All right, so on we go then. That's Q equals IT, V equals IR, and then we've got the two equations that really relate electricity back to the real world. Because what is electricity? It is simply put using electrons to transfer energy around from one place to another, but we use electrons within the wires to do that. So this is an energy system, so we need to know how much energy there is. So the amount of energy is equal to the amount of voltage that you have multiplied by V multiplied by the current multiplied by the time. E equals VIT. Now this is probably a little bit more easily remembered as I times T times V, because ITV is a little bit easier. Okay, so that's current times time times voltage. And as an extension, what you should remember from last year is that power is equal to energy divided by time, which gives me that power is equal to IV, that P equals IV, because the T disappears out of that. Okay, now as a side note then, the voltage is by definition then the amount of energy that is carried by a single coulomb of charge. It's the energy given to each coulomb. So we've gone through quite a bit there, so let's just run that. Let's run that back. What you have to remember is what is charge. So some basic simple ideas here. If we imagine that we have a pile of electrons lying about somewhere like this. Okay, we could count all the electrons, but that would take forever because they're super tiny and the amount of energy they're carrying is ridiculous. So what we do is we group them all together and we get a whole pile of them, and we call that a charge. We call it, okay, this is a group of charges, and when we get a certain number of them, we call it a coulomb. Okay, think if you have loads of things sitting in you have loads of buns in a box, you don't say that you have 24 buns. That's really weird. You'd say you have 2 dozen. The 360p quality should be running out at high definition there, Scorpion. Check your settings. It should be at least 720p. I'm definitely encoding at that, so I'm not quite sure what's going on there. Maybe you're just buffering a bit. Okay, so a coulomb is a group of electrons. Right, simple as that. That's what charge is. It's just the number of electrons you have. Now, what we want to do then is we want to use this little group here, and if I stick some energy into it, now how am I going to stick some energy? Let's make another circle inside that and color it in a bit. Okay, so let's fire some energy on it. Okay, if I fire a whole pile of energy, I wonder if I can make that transparent. I bet I can. Yeah, look at that. Okay, so if I put a large amount of energy in it, then that's a large voltage. But if I put a relatively small amount of energy spread across that same coulomb, that's a small voltage. And that's what we mean. All right, that's what we mean. That voltage is the amount of energy you give to a particular coulomb of charge. And of course, in a wire, there's piles of them. All right, and then your current is how many of these coulombs that you get if you set yourself up in a wire, and I say I'm observing here. I've got my little eyeball and I'm going to look there. So let's grab myself an eyeball. There's something that vaguely looks like an eyeball. Gorgeous. Fill that in black. Okay, not freaky at all. So my eyeball is looking at this point. Then what current actually is I just sit and count, and I go 1 coulomb, 2 coulombs, 3 coulombs, 4 coulombs, and if 4 coulombs pass in a second, that's my current. 4 coulombs per second would be an amp. All right? Hopefully that's okay. So these are kind of the basic equations you need to know. Q equals IT, or I equals Q over T is the rearrangement. V equals E over Q, E equals VIT, or ITV, and P equals IV. Now E is energy, and as such is measured in joules, and P is power, and as such is measured in watts, just as before. And don't get messed up with this, because there's always a mark available for getting the units right. And a horrible examiner, well, not a horrible examiner, but one that's looking to kind of add a bit of difficulty to a question, might give you energies in kilojoules or kilowatts, in which case you need to be able to convert from one to the other. All right, right. On to business then. Once we've got these, we need to put these into some systems. So let's get ourselves a little system. So let's draw ourselves a battery of some description, or in this case we'll actually do a little power pack, because that means I can copy and paste it, which is great. Drawing power packs is about as much fun as taking a razor blade to the back of your head without any guard on it. It's been rusted for about 6 months, but there we go. Maybe not quite so bad. Let's say that's an 8-volt power supply. Okay, so that means that every little coulomb of charge that goes through this power supply is going to pick up 8 joules of energy. And off it goes out into the world, round and back like this. Okay, so this is a dreadfully dangerous situation. This is called a short circuit, because there's a couple of rules that we need to know about electricity. But let's stick a resistor in so that we can chat about those rules. All right, so grab that there, and we'll have fill color. Right, so first things first, this side of the battery is positive and this side is negative. The big stick is positive, the little stick is negative, because everybody likes tall people and nobody likes short people. Tiny people. That's actually not true, but well, it is. Right, so coming out of positive, we have our current. Current flows round out of positive and around to negative. Now that's not actually really what's happening. In fact, the electrons are going from negative to positive, but because of the fact that electricity was discovered before the electron was discovered, we're sort of stuck with this convention, and that's why it's called conventional current. Okay, so running from positive to negative, we have conventional current. Now, round we go like this. I can't believe I'm sitting in my study here pointing at the screen, because I've been YouTubing for long enough now to realize that you can't see me. But anyway, so out of positive, round to negative. And what happens is my little coulomb of charge comes out of here. Let's grab him in there, and he's carrying, let's call him an 8-volt coulomb. He's carrying 8 joules of energy. And he has to go out, and he's pushed out of the positive side and is forced round to the negative side. And the reason that's happening is because as he's coming out, there's another one coming behind him and another one coming behind him, and since they've all got the same charge, they repel each other along. Okay, think very large traffic jam just going round in a loop forever. Right, so round we go into here, and our 8-volt system arrives here. Now this is when we get our rules. Okay, so rules are: 1, current goes from positive to negative. 2, it can't go back on itself. And this is simply because if this little Coulomb down at the bottom tries to turn round, it's actually stuck because there's a whole pile of other ones this way. Everything's moving this way, and that's all there is to it. So you can't go backwards. You can split up, you can change direction, but you certainly can't go back. And 3, you must arrive back at the battery with 0 volts. All right, and then I suppose for the sake of describing this situation correctly, we'll have a basic 4th rule, which is that wires use no voltage. Alright, so traveling from here to here, from this side of the battery round to my resistor, nothing gets lost. Okay, so here's my rule. I have to come out of here with 8 volts because this is an 8 volt battery. I have to arrive back here with no volts. That's our rule here. We must arrive back at the battery with no volts. And I can't lose any of this voltage in the wire. So by logic, all of my voltage must be lost here, inside this resistor. So this resistor is taking 8 volts out. Okay, what that means is it's taking out 8 joules of energy for every coulomb that's going on. And this is fundamentally the difference between a power pack and a resistor. A power pack provides energy to the coulombs, and every other component in a circuit is removing energy from them. And that's the point. All right, happy with that? Good. The top is really blurry, but the bottom is grand. Okay, that is extremely weird. That shouldn't be the case. The setup is kind of how high in terms of top is blurry. Give me a shout in chat there. I'll see if I can move it down. Even if I move it down a bit, is that helpful? Okay, so 8 volts comes out of here. Right, now, that's us. That's all you need to be able to do. We will then say we can later on categorize these things as being different resistances depending on how much energy they take compared to each other. But in this situation, that's basically all the information we can get. We can do a little bit better though. Let's try something a little bit more complicated. So let's copy that so I don't have to draw it again. And this time let's stick a couple of resistors in. So this is this kind of standard series setup. Okay, so we know this is going to be a series circuit because the way to tell if it's a series circuit is take your finger from the positive side of the battery and walk your way, just go along the wires and try to get to the other side. And if you never ever get a choice of which way to go, then it's a series circuit. So even if you're a first year and you're in chat at the minute, you should be doing this in electricity in first year. So this is how we tell that I travel my way along here, then I have to travel through here, then I have to travel all the way through here, and then up through here and up through here. So this is a series circuit because I get from positive to negative, having never made a choice of which way to go. All right, now let's give these some numbers because we want to get on with things. So let's give this a 50 ohm rating. So that's a 50W with a symbol. Yeah, try that again. That's rather annoying. This should be an ohm sign. Okay, that's better. Okay, so 50 ohms there, and let's give this other one over here. Let's give it 25 ohms, just for the sake of keeping the numbers simple, and let's give this 6 volts coming out here. All right, so as we travel outwards, we once again have 6 volts coming out of here because that's a thing, and we have 0 volts coming out of here. And I'm just going to grab my little tool here and grab our rules and bring them over so that we have them sitting for us to refer to. Stick them up there. Okay, so current goes from positive to negative and it can't go back in itself. So here I go, off I travel. So I come out here and I travel through here and I travel through this and I travel through that. So I'm going to have to go through both of these resistors and arrive back with 0. Now the immediate thought is that you might drop 3 volts at each, or you might drop 6 volts here because you arrived there first, as you might think, but that's not actually how it works. Okay, first of all, there's no such thing as arriving first. The entire wire is filled with electrons, so as soon as one moves, all the charges move. So the instant you plug this in, every charge in this whole thing moves. So there's no such thing as a first resistor, second resistor, or whatever. All right, so you need to treat these as if they're both the first resistor. Secondly, they're not going to split evenly. This is a 50 ohm resistor. That means it's got 50 ohms of difficulty to get through, and the 25 ohm resistor has 25 ohms of difficulty to get through. That means that this one here is twice as difficult to get through as this one, which means it's going to be twice as much energy used getting through this. All right, yes, Scorpion, I will do it a little bit later, but at the minute we're just looking at the split of voltage. So if my question was, what's the voltage being used by each of these, I would have to say that this one's going to use twice the voltage, so that's going to be 2 times, and this one's going to be 1 times the voltage. So this is a ratio problem. This is a 2-to-1 ratio. So there are 3 parts. Okay, so 6 volts in 3 parts. So that means that 2 volts is 1 part. Okay, divide both sides by 3. So 1 part is 2 volts. This one's getting 2 parts, so this is a 4 volt system here, and this is a 2 volt system here. All right, is that okay? Now, we can do a little bit better, and Scorpion kind of jumped the gun on me there, but we like the fact that we're thinking about things. What we can now do is we can work out the current flowing through this system, and there's a few ways of doing that, and this is all done using Ohm's law, that V equals IR. Now, Ohm's law is amazing. It is utterly amazing. It works for a whole circuit, or it works between any 2 points in a circuit. In fact, the first statement is redundant because by the whole circuit, I mean between this point here and this point here. That's my 2 points that I'm choosing if I'm doing the whole circuit. But I could choose between here and here. And we're going to do both to show that they work exactly the same. So let's consider between these 2 points first. Okay, in order to do V equals IR, I need to know, I'm looking to find I, so I want to rearrange this equation first. And that's going to give me I equals V over R. And if you hate maths, which you shouldn't, you can create yourself a little equation triangle for that. But be aware, equation triangles do not count for marks in exams. Only once you've written the equation do you actually get a mark. All right, so the current in this case equals, between these 2 points, between X and X, how much voltage is being used? 4 volts is being used, divided by how much resistance there is, which is 50. So I is equal to 4 over 50. Pop that into our calculator and we get 0.08 amps. And that's the current. Now this is a series circuit, so we would expect 0.0 amps to be the same everywhere, and we need to be clear on that. This is a series circuit, so as soon as I get a current here, it's the same everywhere. So the current is 0.08 amps anywhere I choose to go. So if I've just measured the current between those 2 points, but it should be the same as the current here, as here, as here, as anywhere in the circuit. That's the beauty of series circuits. But let's make sure that's true. So what we're going to do is we're going to do for the whole circuit. So between this point here all the way around to this point, we again want to use I equals V over R. Now, between those 2 points then, the voltage being used between those 2 points is all the voltage. So that's 6 volts. Divided by the resistance, the total resistance that has to be experienced by this little coulomb traveling through, which is a full 75 ohms, because it'll hit the 50 and then the 25. So I then equals 6 divided by 75, and lo and behold, we once again get 0.08 amps. And in your own time, you can have a check and see if 2 over 25 is also 0.08. Okay, so it's hardly going to be a thing. All right, so that's series circuits. And if you want to get the total resistance in a series circuit, it is really straightforward. It is R total equals R1, the resistance of resistor 1 plus the resistance of resistor 2 plus the resistance of resistor 3 if you have it, and so on up until however many resistors you have. All right, so you can have a million resistors. You just keep adding them on, adding them on, adding them on. Provided I never get a choice, I keep adding them together. Happy? I hope so. So let's make life a little bit more difficult for ourselves. So once again, I'll grab my little power pack, copy that out, and go to here. Right, now it's game time. We're going higher tier, or we're going triple award, or something along those lines. All right, so let's get ourselves up to the properly difficult level. All right, so difficulty level 1000, this is your exam question. It's question, say, 4. You've done a bit of static electricity, you're feeling good about yourself, and they've decided, right, it's time to hit you in the face with something because you're getting a bit too cocky. So here's your setup. We've got a resistor here. We're going to grab another resistor and we're going to put one on each of these parallel branches, and we're going to get you to sort some stuff out. Okay, so we don't want that. We want a line color of black. So there's my resistor, and I'm going to whack another resistor down here and whack another resistor up here. Cool. So let's go to it. Pop in here. Let's give this 100 ohms. And here we're going to give this 50 ohms. And then here we're also, no, we're not going to do two the same. That's too handy. Let's give this 20 ohms. And we might end up with some horrible maths, but that's all right. We'll make it 30 ohms because that should hopefully make the maths a little bit less horrible, but 30s are never good. And let's give you 10 volts to play with. Now, I have absolutely no idea how this is going to turn out, so this should be interesting. We could end up with numbers all over the shop, but that's what we're here for. All right, now what we want to do here in this one is we want to say, right, first of all, how would I measure how much voltage is going through my 100 ohm resistor? So what we do is we have to put a voltmeter in, because voltmeters are what measure voltage. So get a little smiley face down there and get a V here for a voltmeter. And a voltmeter will tell you anything that that you want to know, provided it has its legs wrapped around the thing that you want. Okay, so imagine it's that it's a little person here, 2 little legs hanging out, and provided you stick its legs around whatever it is you want to know about, it'll tell you all about that. So this is going to tell me about everything that's going on as you go through this 100 ohm resistor. Now there is a better way to remember that, but this is a PG, family-friendly channel, so we'll leave it at that. But you should remember. All right, so I want to find the voltage being used here. And let's say I also want to find the current that's being used in the whole circuit. Now a current, if I want to have a current, I use an ammeter. And an ammeter is ammate. Terrible, I know. And therefore it sits beside whatever it is you want. So it should always be in series. It shouldn't have any legs hanging out of it. Okay, it should always be stuck on a wire that already exists. Happy? Modular Friday? Probably not. No. Well, Shane, maybe. Okay, so on we go. Demonetized Scorpion, absolutely spot on. Yeah, if it was monetized in the first place, maybe. So let's get sorted out here. We've got 10 volts going on. We've got 100 ohms going here. We've got 50. We've got piles of stuff going on here, and I don't know where to start. I'm having a complete and utter breakdown. So the reason I'm having a breakdown, the reason that this is different, is because of this section here. Okay, this is my annoyance here. I can't deal with this. I haven't been given the skills in this video so far to deal with this section. All right. So let's get rid of it. What resistor would replace this 50 and 30? And what we can do is we can use the parallel resistance rule. Okay, and the parallel resistance rule says that 1 over R total. Okay, so 1 divided by the total resistance is equal to 1 over R1 plus 1 over R2 and so on for every resistor we need. Now we're only going to use R1 and R2 because I'm only trying to get rid of this section. Okay, because this isn't parallel. Okay, I have no choice. I have to go through this 100 ohm resistor, so therefore it's a series resistor. It has the series rules. But this one here, when I arrive at this point, I can either go this way or I can go this way. As a result, I've got a choice, and as a result, I'm using parallel rules. Okay, so here I go, 1 over R total. So 1 over R total is equal to 1 over R1, which is 50, plus 1 over R2, which is 30. Okay, so 1 over R total is equal to a 50th plus a 30th. Now you get your calculator out on this one. You don't bother trying to do that, but my calculator is a little bit in limbo at the moment, so let's have a look at that. So that's going to be 3 150ths plus 5 150ths, so that's 8 over 150. All right, is 1 over R total. And you'll be able to simplify that down because that's certainly going to at least divide by 2, but that doesn't matter. The important bit here is that's not the answer. And you should know that's not the answer. Like 8 over 150 is a really small number, and 50 and 30 are not that small. So you don't get tricked in an exam to go, oh, 8 over 150. It's not. It's the other way up. 1 over R total is 8 over 150. So R total is the inverse of that. That's 150 divided by 8. Okay, and that goes straight into your calculator as well, and we go 150 divided by 8, and that gives me 18.75. Because I do have my phone handy as a calculator. So 18.75, and we should be able to check that. Does that seem reasonable? Yeah, it seems reasonable. Okay, that the total resistance of a parallel section should be a little bit less than the lowest resistance. Okay, and it shouldn't be ridiculously less. All right, so that's about right. So what I can do now is, in my brain, I can replace that with a single resistor. Okay, so instead of having my 50 and my 30, I'm going to replace it with a single resistor, and that resistor has a value of 18.75. So mentally I can do that. And if you want to, draw it at the side. Okay, but I'm no closer to getting A or V here. Now we can do this by ratios, but that's unpleasant. So what I'm going to do is I'm going to use Ohm's law for the whole circuit. So I'm going to do X here and X here, because I have the voltage for the whole circuit, and if I think about this as a series circuit, I have the whole resistance of the circuit. So I can do I equals V divided by R. So I equals 10 divided by the total resistance, 118.75, because now I can treat it like a series circuit. So I is equal to, and once again, back to your calculator, no heroes on this exam, make sure you get the answers in and right. So 118.75 goes into the calculator, and we end up with 0.842 amps. Alright, and that's part one sorted out. But even better, if there's 0.842 amps going through here, then logically it must be going through here as well, because there's no way that they could have split up or anything, which means that it must be going through here, which means it also must be going through this resistor here. So 0.842 amps is flowing along here. And now I can use Ohm's law between this point and this point to get the voltage. We get V equals IR. That V is equal to 0.842 multiplied by 100. So V equals 0. That should be an O. Yeah, it should be an O. I knew that was wrong. Right, 0.0. Watch your calculator, people. Watch your calculator. Multiply by 100, giving me 8.42. All right. I can also go a little bit more on this, but I haven't been asked to. If I know that that's 8.42 volts here, then I know that whichever route I take through this path here is going to have to use the rest of the voltage. Remember my rule, I must arrive back with 0. I've used 8.42 here, so that means I must use 1.58 volts, regardless of which way I go through this. So therefore I get 1.58 volts here, and 1.58 volts coming out of this one as well. And I'll get rid of my little mental arithmetic thought here. And now I've sorted this whole diagram out. Okay, and this is why, ladies and gentlemen, that the voltages across any branch in parallel are always the same. Because if they were different, it would be possible for me to arrive back at the bulb or at the battery with a number other than 0. They have to be the same. We good? All right, excellent. At 20:58, I did promise half an hour. That may be gone, but we're going to take a quick look at graphs. 5 minutes on graphs. Right, your standard graph going on in electricity looks like, well, it doesn't necessarily look like this, but generally speaking, it looks like this. Okay, with I up the side in amps, that's current up the side in amps, and voltage across the bottom in volts, so V in volts. And that's a perfectly fine way of labeling it, by the way. That's grand. And anything that obeys Ohm's law is said to be ohmic and does this. Okay, if you do this, you are ohmic, because Ohm's law says that the current is directly proportional to the voltage for a constant temperature. So phew, away we go. Directly proportional line, straight line through the origin. That's an ohmic conductor. The steepness of this line, though, is the gradient of this line is not the resistance, and that's really, really important. That the gradient is not the resistance. And I'll tell you why. R-E-S-I-S-T-A-N-C-E, resistance. That the gradient of this line, M, is equal to I over V. Yeah, rise over run. But if V equals IR, R equals V over I. Okay, so the resistance is the exact opposite of this gradient. So the best way to think about this is actually that the gradient can be considered to be the conductiveness, if that's even a word, of the material. Right, the steeper the gradient of this graph, the more conductive the material becomes. So this one is super conductive. It's really conducting, because I only need a really small voltage to make a pile of current. I need a small amount of energy to fire loads of coulombs around this thing. This is really low conductive, because I need a huge amount of energy per coulomb to make even a tiny current. So this, therefore, is a high resistance, and this is a low resistance. Okay, so yes, Matthew, the resistance on this one would be the run over the rise. Be careful though, make sure it's I against V. Okay, so this is conductiveness that we're looking at here. And most ohmic conductors will play like this. So if I was to say, here's two materials, which one of these is more resistive, then this one here is more resistive. Okay, and why is it more resistive? Because it has a lower gradient. Okay, so in IV graphs, your gradient is the opposite of resistance. So more resistive means less gradient. Okay, you're getting less for it. Is that all right? Now, there are a couple of specific graphs that you need to know. For double award, it's just the one graph, okay, that you really need to get onto, which is this one here. That if you have a filament light bulb, okay, so that's the standard old style light bulb. My apologies for my phone going in the background. That's 2 weeks in a row I forgot to put it in silent. Normally I'm so unpopular it makes no difference whatsoever. I imagine it's Vodafone telling me that my data limit's up. Anyway, or my wife telling me to keep the noise down. One of the two. Filament lamps are a little bit funny, because they do what Ohm's law tells you not to do. Ohm's law says that the current is proportional to voltage for a constant temperature. But an old style lamp does exactly not that. Its entire purpose is to get warm. It heats up, it glows, it goes white hot, it gives out light. That's the point. Okay? How do I draw my line so straight? I've got a straight line tool. I'm cheating, seriously. So watch this for bad drawing. In a filament lamp, what happens is that as it heats up, your ions inside vibrate more. That means your electrons get hit more by as they try to get through the wire, which means that your resistance goes up or your conductiveness goes down. So what happens is this. You get a graph that starts off sort of straight, but then very rapidly curves off like this. Okay, so it starts off. If we look at this in a series of straight lines, it starts off kind of conductive, then less conductive, then really not conductive. Or it starts off with low resistance, but as it heats up, it gets more resistance, and then lots and lots and lots of resistance. I don't know what happened to my keyboard there. Anyway, and of course we can put current through it the other way. So this is why we've got this positive and negative curve here, because we get the exact reflection the other way. If I try to send current backwards through it, the exact same situation is a thing. Okay? Happy? Good. So that's the filament lamp. And if you're double award, this is where you get to stop thinking for a couple of seconds. For triple award, though, you have something else. You get to have the diode, which is important because it makes use of this kind of multiple quadrant graph. And again, I waved at the screen. Stop doing that. Right? In a diode, what happens in a diode is what it does is it stops electricity going a particular way. So normally, a normal diode does this. Okay, that you apply a little bit of voltage and it takes a minute to get going, and then kind of goes off like that. Okay, which isn't very interesting. It's not particularly different to a normal conductor. But what you would expect from a normal conductor is if you did it the other way, you would get this kind of situation going on here. That would be a normal conductor. But in a diode, what it does is it stops current flowing backwards through it, or whichever way you want. We'll call it backwards. So what you end up with is this entire section here just as a flat line. And that's it. Okay. The one that starts at a really high resistance and then lowered in your test, that is the Ntc Thermistor. It's interesting. We may as well talk about that, Matthew, whilst we've got it. Okay, so an Ntc Thermistor is useful to learn because it is sort of the exact opposite. That what an Ntc Thermistor means is it's a negative temperature coefficient thermistor, which means that like everything else in kind of electricity tends to be, if it heats up, it gets more resistive. An Ntc Thermistor does the opposite. Okay, as it heats up, it gets less resistive, and that's very, very interesting. So heat and current are generally speaking related to each other. So we can sort of work out what this means. That if we have a current here, as the current gets bigger, your resistance is going to get smaller. Okay, so your gradient is going to get less and less and less and less and less. All right, and if your resistance gets less and less and less, you're going to need less and less voltage to push things through. So your gradient is going to change. Is that okay? Do you understand that principle? Now we can draw this kind of concept in lots and lots and lots of different ways. But the basic idea for an Ntc Thermistor is you start with low temperature and therefore kind of high resistance. So you end up with this thing like this. But then high resistance, kind of like this. But then as time goes on, you get this curvature effect that as the current gets bigger and bigger and bigger, that you get less and less and less resistance. So your gradient gets gradually steeper. So you end up with this type of situation. You end up with a kind of curvy job like that. Is that all right? Okay, good. And that's the thing. Now, normally speaking, what you get in exams is you don't get asked to draw these things. The filament lamp is likely to be the one you get asked to draw. Most of the rest are you get asked to interpret what's going on. Okay, and the key thing there is to just go, right, what's happening to the slope of this graph? If the slope's getting bigger, it's getting more conductive. If the slope's getting less, it's getting less conductive. And then you run that backwards in your head and go, right, if it's more conductive, it's less resistance. If it's less conductive, it's more resistant. And that's kind of it, really. Electricity, not particularly difficult. Once you get your head around the concept, you're grand. And then finally, the things that affect the resistance of the wire. Okay, one is length. Okay, longer wire equals more resistance. You've got more stuff to get through, so you're more likely to get involved in a collision, you're more likely to lose energy. 2, cross-sectional area. Okay, bigger area equals less resistance. Okay, and in fact we can do better. That multiplying the area by 2, so times 2 area means that you get a resistance of a half. Multiplying by area by 4 gets you a resistance of a quarter. Doubling the length, times 2 length, gives you times 2 resistance. They're proportional to each other. Temperature. Depends on the material, but generally speaking, bigger temperature equals more resistance. Okay, not necessarily a 2 times system there, but bigger temperature generally means more resistance. Your ions are vibrating more, you're more likely to be involved in a collision. And as soon as you talk about collisions, you're talking about ions vibrating inside them, little electrons trying to get past. Anything that makes it more likely for them to crash is bad. And number 4, the material. Okay, if you get different material, wait for it, you get different resistance. And that's the best you can say without knowing what the material is. Some materials are great, like gold's a brilliant material for conducting electricity, and wood is not particularly good, air's not great. So change the material, you get different resistances. And that's you. Don't forget to look up the experiment on how you would actually go about doing this. If you're asked an experiment, if the experiment says how would you check how cross-sectional area affects resistance, then what you would do is you would change the cross-sectional area, maybe have different wires of different cross-sectional areas plugged into a circuit that measures voltage and current. And you would then need to keep the length, temperature and material the same. So these are your 4 variables, and at any time you should only be changing one of them. I'm thinking 6-mark question here on this one, and that's how it's done. Right, I've kept you long enough, folks. I said half an hour. We've been on 40 minutes. I really appreciate you coming along. I will leave you with a little bit of advice from one of my favorite running motivational speakers, who says that this is in reference to kind of talking about revision. If you're sitting there thinking, oh, I'm tired, have I done enough? Maybe I should do an hour, 2 hours. How much revision do I need to use? Here's a thought, that when a cheetah is hunting a gazelle, the cheetah does not think, how long should I hunt the gazelle? The cheetah hunts until it gets a gazelle, and it doesn't stop until it gets one. You have a day and a bit before what I reckon is the most important exam that there is. So go hunting. If you want to go and have a wee nap, then you want to sleep more than you want to be successful. All right. Good luck, everybody. I know you'll be brilliant, and always remember, physics rocks. It's true.